Before we begin the specifics, any comments, any questions, anything at all so far? Something that you thought you understood, but you realize you really didn't. Everything is fine. Okay, let's move forward. We started this towards the end of the last class, analysis of reactions that involve reactive species. So it provides insights on their effects, we said, and we also recollected that the basic tools or the frameworks that are available for analysis are the ones that we know well, thermodynamics and kinetics. Okay. So to just make sure that all of us are on the same page, please go to your Moodle page, and there is set of self-evaluation questions on thermodynamics. Should I add you to the Moodle page? That might be a little better, isn't it? So that you can keep track of. Yeah, there will be resources that are coming up and so on. So take about 10 minutes, 10, 12 minutes. Yeah, there are 7 questions. If you recollect your thermodynamics, those you should get all of them done in about 5. But yeah, let us give about 10, 12 minutes. Right. Are you able to access your Moodle? You think? Okay, fine. So please check. There is a self-assessment quiz kind of a thing, a set of questions. You don't have to look at it beyond a set of questions. It will give you the answers right away. Most of the information we have started learning from our school, whatever is needed to solve it. But people who have done an engineering background, who have an engineering background, would have done multiple courses on that. So they might find it a little easier to solve, to answer those. See whether you are able to answer it. And if needed, there are courses in NPTEL and otherwise on basic thermodynamics. There is a course of my own with Sanjeev. Sanjeev did the statistical part and I did the classical part. If you look at the first couple of lectures, that is good enough. It is available on NPTEL. It's running this time, but you can always watch the videos. You don't have to become a student to watch the videos. You can always watch the videos. Pardon? Yeah, NPTEL is available online. If you go to nptel.ac.in, all courses are available anytime. So that's not a problem. So if you look for my course on thermodynamics for biological systems or something like that, it will say thermodynamics for biological systems, classical and statistical aspects. So that course, a couple of lectures, first lectures are good enough to pick up the necessary background to answer these questions. Okay. And then of course you'll need practice to become more comfortable with numerical solving and so on, solving of numericals and so on, but that's okay. You can pick up. Okay. Okay. Among the others, did anybody have any clarifications? Something that's not clear? So all could answer all questions. Right or wrong doesn't matter. You know the right answer now, so you can always go back and figure out where exactly that happened. See, forgetting is very natural, okay, which students accept after a very long time, typically. They give it as an excuse, but they never accept it. So, because forgetting is natural, we have books, we have notes and so on and so forth, so that we can go back and pick up, brush up whatever is necessary when the need arises. I always do that. I cannot remember everything. Some of course are blessed with very good memories. They have special skills, that's fine. That's probably a very small percentage of the population. That's okay. Okay, so any questions, comments on this, on the background? You're all fine, okay. The thermodynamic information that's relevant to us for the reactive species reactions is pretty much entirely available in the form of a table of reduction potentials. Okay, once you have this table, you have most of the information that we need, thermodynamic information that we need for our purposes. Okay. You might have read about this earlier in school certainly, but let us spend a little more time on this because we need this for our purposes. The reactions that, I mean, we will get to that in a little bit. As a part of the discussion, we will spend more time on the table of reduction potentials. The reactions that involve reactive species, especially the reactive oxygen species, are reduction reactions obviously, or oxidation reactions, or reduction oxidation reactions. Okay. So, these are the kind of reactions that typically the reactive oxygen species go through. Now, again in a recall mode, we will have to be clear about this. Reduction involves a gain of electrons or an addition of hydrogen, as we saw in the last class, I think a couple of classes earlier. Oxidation involves loss of electrons, and the species gaining an electron is to be reduced, just the ulta thing. And the species losing an electron or electrons is said to be oxidized. And the mnemonic that we saw a couple of classes earlier, Leo the lion says Gur. Leo stands for loss of electrons is oxidation, LEO, and Gur stands for gain in electrons is reduction, GER. Okay. Any clarifications on this, these basic statements, basic definitions essentially, and the type of reaction? Right. So, we are setting up perimeters for analysis. Now, for analysis and use, the reduction and oxidation parts of the redox reaction are typically separately taken, okay, because it is easier to get good information on them. This is essentially for better conceptual understanding and manipulation. The reaction occurs as a redox reaction, it never occurs, rather, yeah, there could be reduction, there could be oxidation separately. The electrons are taken care of appropriately there. But for a redox reaction, although we write them separately, they always occur together as a redox reaction. We are separating the reduction part and the oxidation part. So, such reduction or oxidation parts of a redox reaction are called half reactions. They are conceptual, right? They do not exist, rather they do not exist separately, they are conceptual. And we have already seen this reaction or rather these set of reactions, right, which involve oxygen going to water after 4 electron reduction through superoxide, hydrogen peroxide, hydroxyl and water, right. So, we will take one of those reactions. Let us consider the first reaction separately written, oxygen getting reduced, electron addition giving you superoxide, right. So, here it is a reduction reaction because it involves addition of electron. If this reaction is taken to be a part of an electrochemical cell with the standard electrode, right, we will see, we will recall what a standard electrode is. So, you have this half reaction, you pair it with a standard electrode, and then if we measure the voltage that those two put out, it shows that that can be a source of energy, and that is basic electrochemical energy, right. So, therefore, there is energy associated with the reaction. Right. Let me tell that I am giving you, there is certainly energy associated with the reaction, and that is what is coming out as a part of this. There is a conversion of chemical energy to electrical energy in this case. The standard electrode, if we recall, is a platinum electrode dipped in a 1 molar solution of hydrogen ions and exposed to pure hydrogen gas at 1 atmosphere pressure and 298 K. Okay. You go to any standard textbook, all these definitions will be available. So, you can do that. So, this is the standard hydrogen electrode. It is a platinum electrode dipped in a 1 molar solution of hydrogen ions exposed to pure hydrogen gas and standard temperature pressure. Okay. So, we are combining this with that, and as a reaction you could write it as 0.5 hydrogen giving you hydrogen ions and electrons, very simple. So, this causes an electron flow from an electron donor to an electron acceptor, and that electron flow is nothing but current. which can be measured as a voltage also. The potential of the standard electrode is assigned a value of 0. So, that is the standard reference that we do in all our thermodynamic things. Something is chosen as 0 arbitrarily. Okay. So, you choose the potential that is associated with this half reaction as 0. Okay. So, there is a potential here, there is a potential here, and therefore, a potential difference arises between the two when electrons flow from one to another, when they are coupled together. Any questions, comments on this? Now, the standard reduction potential of a half reaction indicated as E naught, right. I might be following a terminology, I am following a terminology that is standard, but the terminology itself is different between different books. So, just follow this. E naught is the voltage measured when the half reaction under consideration is paired with a standard hydrogen electrode. That is why it is called a standard, because it is assigned a value 0, whatever voltage that comes out is can be directly taken. Another terminology here, again the same reaction, oxygen getting reduced to superoxide, okay, oxygen plus an electron giving you superoxide. It is represented as this slash this species. What does that mean? This is the reduced species, this is the oxidized species, right, or rather this is the, this is getting this is you are adding electron to oxygen, right, and it results in superoxide. Superoxide oxygen is getting reduced. So, reduced slash oxidized is what you write. Okay. So, this is a standard way of writing half reactions, remember this. So, if this is coupled with a half reaction of a standard hydrogen electrode in an electrochemical cell at physiological pH, which is pH 7, the electrical potential difference associated with the reaction would be different. Why? Because the standard potential is at a pH of 1 molar hydrogen ions, and therefore, a concentration of 1 molar hydrogen ions, and therefore, a pH of so, if you have 1 molar concentration of hydrogen ions, what is the pH? 0 minus log of the hydrogen ion concentration, right. So, hydrogen ion concentration is 1 log to the base 10, and therefore, your value is 0. 0, it is not physiological, nothing in the cell can happen at 0. So, a typical trick, we define our own pH standard, which is the physiological pH of 7. The electrical potential difference associated with this reaction is minus 0.33 volts. Okay. So, this is called the standard reduction potential from a biological context, right. So, everything else being the same except the pH being 7. And the standard reduction potential E naught dash. E naught is at pH 0 or a 1 molar concentration of hydrogen ions. The value at pH 7 is E naught dash. Okay, we work with E naught dashes. The assumption here is that all chemical entities of relevance except hydrogen ions are present at 1 molar each in standard conditions. And since we are interested in biological systems, the pH 7 is the physiological pH of 7. If you do this, and people have done this, people have measured this multiple times and they have compiled, there are many compilations. This is from your textbook. In my book, I have used this, I have used from many other sources and put together a much longer list. You need to wait for the book to come out to get that. So, here you could see the half cell written as species slash species, reduced species, oxidized species, and the standard reduction potential, this is the E naught dash at a pH 7. So, all these values are given. Okay. So, this is from your textbook, the most recent edition of it, the 5th edition of it. Any questions? Any questions? No. Okay. Local clarification was good enough. Okay. So, these are biologically relevant reactions that happen in the cell, as you can figure out. So, this is a reasonably complete list which you can use. I have uploaded this onto your Moodle page, essentially picture of this onto your Moodle page. You can use this for whatever calculations you want to do. Okay. So, yeah, whenever needed you can access the Moodle page, nothing. That's okay. Here it says, yeah, data largely selected from extensive compilation by Buettner. Data are corrected to a pH of 7 unless otherwise stated. They are E naught dash values rather than E naught values. Values quoted in the literature often vary slightly. For each couple, the oxidized species is on the left and the reduced species is on the right. So, in terms of species, oxidized slash reduced. Okay. So, that's good to remember. In terms of species, you are writing the oxidized species first slash reduced species, and that represents that half reaction. The electrons are not written there. A half reaction with a negative E naught dash value will have a tendency to release electrons, and a half okay. So, if you look at the values here, the standard reduction potential, it is from minus to plus. Okay, it is deliberately arranged in this fashion because the values with a relatively more negative value will release electrons to a half reaction with a relatively more positive value. That is all. Okay. Does not mean negative means always will release. The first reaction will always release in comparison with all other reactions, right. So, minus 2.84 would release reactions to minus 1.8 as well as to 1.06 and so on and so forth, all reactions below it. Okay. So, that is what this is. Irrespective of, that is what I meant, irrespective of positive or negative values, a half reaction has the ability to reduce all systems or all half reactions with a E naught dash value higher than it, right. That is what I mentioned. So, this can be viewed as an electron tower moving from top to bottom, the electrons moving from top to bottom. That is a very nice picture to have. Whatever electrons are in the top half reactions will go down easily to the bottom half reactions. A half reaction with a positive E naught dash value or a relatively positive E naught dash value will have a tendency to accept electrons. And again, same thing, irrespective of the positive or negative values, a half reaction has the ability to oxidize all systems with a E naught dash value lower than it. Okay. Lower numerically, so more negative means it will be higher on the reduction potential table, and it will oxidize on them. Any questions, comments on this?
So that the magnitude of E naught value should be greater than the half reaction, so that half reactions can reduce that.
Not the actual number, the negative is counted. See, for example, minus 2.84 has the lowest value, okay. And in this table, in these set of half reactions, you could find another half reaction which has a more negative value, and this reaction OH dot sorry H plus H2O has the highest value. So, any reaction that is numerically includes the sign, right. So, minus 2.84 is much less than any other reaction below it. So, minus 2.84 will release, any other reaction below it will accept. Similarly, let us take something in between, NADH, yeah, that is a nice reaction to take, standard reaction, minus 0.32, a nice value to remember also. So, this half reaction will donate electrons to all other half reactions below it, but can accept electrons from all other half reactions above it, that is all. And then you work out the oxidized reduced, whichever you want. Just if you work that out, remember that Leo the lion says curve. That's all. I never go beyond that, otherwise it gets very too confusing. Okay. Any other comments, questions? Note, E naught dash refers to the standard value, which means the following conditions are met: temperatures standard 298 K, 25 degrees C, pressure is 1 atmosphere, concentrations 1 molar for all species involved except hydrogen. What's the concentration of hydrogen ions? In this case, E naught dash, pH is 7, very good. So, 10 power
10 power minus 7.
10 power minus 7, 10 power minus 7 molar. Okay. So, minus log H plus, remember, yeah, I know log calculations are not that, that frequent as any other calculations. So, but get used to this, a very standard interview question. So, most falter at this, and they falter at this, they are out. So, they don't know what they don't even know what pH is done. So, okay. So, this is the conditions under which E naught dash value is valid. However, if the temperature and concentrations of interest are not the above standard values, which will normally happen in the cell, you cannot have 1 molar of each, right, and the temperature could vary. Temperature could vary according to the temperature that is needed for the cell. The cell could be under temperature stress, whatever. So, if that happens, what do you do? Pardon? What do you normally do? Do you recall? You use some well known equation. Nernst equation, right. So, that is what allows you to work with other concentrations. The effective reduction potential at actual conditions, which means essentially the concentrations are different, the temperature is different. Pressure 1 atmosphere is taken, there are ways to correct for it also, but usually that is not a concern. For biological systems. So, we do not look at that, but there are ways of correcting it. You can put in a pressure functionality also. So, from the Nernst equation, you know that E dash, which is the value of the actual conditions, E naught dash is the standard value at standard conditions. So, E dash equals E naught dash plus RT by NF ln of species with lesser number of electrons divided by species with higher number of electrons. You might want to write this down. Yeah, you've seen this multiple times, even in the transport course you saw this. So, this automatically gives you the relation to a way to get E dash value from the E naught dash value, and this would be much more relevant for all cellular calculations, because you are not going to have 1 molar of the various substrates that are present there, substrates, products and so on. Of course, R is a gas constant, N is the number of moles of electrons transferred. So, you looked at the value of all in various different units, the value of the gas constant in one of the questions. N is small n, sorry. This has to be small n, the number of moles of electrons transferred in the process. And F, of course, is the Faraday's constant, 96,485 coulomb per mole of electrons. So, essentially, Faraday's constant gives you the conversion factor between the electrical basis and the chemical basis, as we saw in the transport course. Okay, fine. It could also be joule per volt per mole of electrons. So, you could write it in different units and so on. Because it's coulomb, you convert it into energy, you will get joules and volts and so on and so forth. Okay, we are looking at energies involved. The Gibbs free energy, the energy generated or consumed in the process of electron transfer, that is what we are getting at, is related to the standard reduction potential in the simple fashion. Delta G naught dash equals minus NF delta E naught dash. So, an direct way to convert the standard reduction potential differences into the energy that is associated with that transfer, right. So, that is the chemical energy that we are talking about. So, this can be used if the concentrations of all species are at physiological pH, sorry, if the concentrations of all species at physiological pH is 1 molar. And of course, if they are not, then you can always use delta G dash equals minus NF delta E dash, which is the value at different concentrations and or temperature, and you know how to convert between E naught dash and E dash from the Nernst equation. Okay. Now, for the remainder of this class, 10 minutes left, right? Okay. For the first 5 minutes, you might need to use your the information on the Moodle page, and you could search the net and so on and so forth, solve this problem. Find the Gibbs free energy associated with electron transfer from oxygen to hydrogen peroxide. Okay, people, let's look at the solution and finish there. Hydrogen peroxide formation from water can be represented by the following reaction or chemical equation: oxygen plus 2 electrons plus 2 hydrogen, 2 electron reduction, right, giving you hydrogen peroxide. So, this is the complete equation which involves the electrons and hydrogen ions. Okay. So, whenever you analyze these things, make sure that you write the complete equations, including the electrons and hydrogen ions. Important for many different systems, even when you go and do some metabolic systems biology analysis, you need to make sure that all these are properly involved, it is charged balanced properly, and only then can you get appropriate analysis. The above can be obtained through addition of the following half reactions, because we have our data in terms of half reactions in our reduction table. That is what we need to match it with. The half reactions are this, obviously oxygen plus electron giving you superoxide, the standard reduction potential at pH 7 is minus 0.33 volts from the standard reduction table, and this reaction superoxide plus electron plus hydrogen ions gives you H2O2, and the value here is plus 0.94 volts. Okay, you can check, you just add these two, you have superoxide on this side, superoxide on this side, cancels out, you have 2 electrons both on the same side, so that adds up, 2H plus remains, H2O2 remains here, which gives you this reaction that you want. So, that is the way we typically check whether you have the right set of half reactions. So, once you have this, it is straightforward. We use the rather energy information that is available in the table that has come up here. The reduction potential is not an extensive property, it is an intensive property. Okay, that is one of the reasons why we reviewed that concept, and therefore, the number does not matter, the amount does not matter. It is like temperature throughout the system, as long as the system as well makes the temperature as the same, right. So, we cannot merely add the reduction potentials to get the reduction potential for the needed process. Delta G is an extensive property. Okay. So, you need to convert the standard reduction potentials first to the Gibbs free energies and then take a difference. Then it is straightforward, you can do algebraic additions, okay, whereas standard reduction potentials you cannot. So, if you do that, for this you have E naught dash is minus 0.33 volts, delta G naught dash is minus NF E naught dash, So, which will turn out to be 31,840 joules. Right? You might want to write this down in case you are writing it down. They will finish in a minute or so. Right. So, essentially we are converting the E naught dash values before algebraic manipulations. And for this half reaction, if you convert the E naught dash value, we get delta G naught dash as minus 90,695.9 joules. And therefore, for the needed process, delta G naught dash is 1 minus the, or we add those two reactions to get the final reaction. If you recall, these were the two half reactions. We needed to add these reactions to get this reaction. We needed to add these half reactions to get this. And therefore, we need to do the same for the delta G naught dash values too. If you do that, you get minus 5.886 into 10 power 4 joules. Recall Coulomb volt is nothing but joule. Therefore, in electrical terms, 1 joule is the amount of energy needed to transport a charge of 1 coulomb through a potential difference of 1 volt by basic definition, and Gibbs free energy of the process is negative, and therefore, the process is spontaneous. Right. So, this amount of information we get just by looking at the numbers that have already been generated for various fundamental purposes by many researchers. Okay, we always build on that. That's the power of fundamental information. We can use it whichever way we want it, as long as we use it appropriately. Any questions or comments on this? And also note, with redox reactions, the number of electrons in half reactions may need balancing. Then you need to go back to that calculation first and then convert it into delta G, and then any questions, comments? Okay. If not, let's finish today. We'll meet again on Monday and look at another problem to get more comfortable with using these principles, and then we'll move. Okay. Okay. See you on Monday then. Bye.